Hey everybody, we're going to continue down the path of transactional memory. I have this little dog right next to me. He's thinking about bolting since he hears the adult voice. Hopefully he stays put. But I want to meander a little bit because I want to try to explain why transactional memory or something in C++ or programming languages just in general is necessary. And yeah, maybe this is in conjunction with things like asynchronous operations. I, I'm not sure, but I want to first start with the state of transactional memory in C++ because I got a little bit of an update there. And I want to talk a little bit about this paper that Hans Bohm and I wrote a decade ago. And then just my general view of the path forward for parallel programming or something outside of GPU systems. Okay, so piece number one, somewhere here, we go, is this thing. Oh, here it is. The update that I have from some of my transactional memory friends in C++, the current status in C++ is we have a greatly simplified TM proposal. I'll drop the link to that in the comments below. It was originally intended to be version 2 of the technical specification. The intent was to have something that was more likely to get implemented and make it essentially easier to implement. And I've seen this reduced transactional memory light or something proposal. I just forgot about it for a lot of balls in the air in my head. So also they're sharing that they were making forward progress, but then there are some, looks like standardization complexities that happen in real life, and that kind of slowed things down a little bit. So that's a little bit of the current state of transactional memory in C++, and then we'll see how things move forward. But while we're looking at that, I wanted to switch now real quickly to give a little bit of an explanation on why I was sort of highly compelled by transactional memory and my views sort of generally as a scientist. So as I think I've mentioned in the past, the way I kind of think about things is I just try to look at stuff and then just kind of ask general questions like, do I think this will work? Do I think this is too hard? Do I think this is too simple and it's not getting at the heart of things? And I don't know that I have any kind of monopoly on what is right, what is wrong, but I definitely don't have an agenda. So I don't come out of the gate like I already know the answer. And I'm not influenced by, and one of the biggest things that I do is I tend to not be influenced in any way by like what's fashionable, what's trendy, what big tech is peddling. In fact, if big tech or some big marketing movement is happening for something, I usually go the opposite direction because I generally think that if the technology is super powerful, then it kind of sells itself, right? Like I don't remember any advertisement for Git or Linux, but it kind of feels like it's everywhere now, and that makes sense because the technology is really powerful. But I do hear a lot of hype about large language models, and it makes me pause and ask, why is there so much marketing hype about this? So along the same lines, when I was first introduced to parallel programming, as I think I mentioned, I thought that it was just sort of like impossibly hard. And that was after, what's that after? I think that was after I had written quite a bit of code. And I think I had a pretty good handle on it. So I'm not talking about hard as in, I think a lot of people might think about hard. The way as we've discussed before, I tend to think about things like there is, there tend to be these sort of two general ways to think about things. There's like this subjective view, and then there's sort of this objective view. And the subjective view on stuff is more in that space of it's it has like a difficulty rating, and that can go from easy to impossible or something. This is kind of just like the way you feel about it, right? And then there's sort of this objective rating, which is similar-ish to difficulty, but it's more in objective reality-ish. And this is more about, we'll just call it complexity. And on the one end, you have that it's very simple. And then you have something that is, let's call this, I don't like these hyperbolic adjectives, but let's call it highly complex because it's more complex than just normal complex, whatever that means. I don't know. I don't. There's complexity and nuance, maybe. I'm not sure what I'm trying to say here, but basically, in this side, there's like not many things, and then over here on the complex side, there's a lot of stuff. There's a lot of things, and from the difficulty lens, depending on your expertise of something, it can be easy and it can be not easy. So, for example, one of the things I do is I'm on the electric unicycle, and right now, because I've been doing it for a while, I really enjoy it, and I wouldn't say that I've mastered it, but it's not hard. It's more just enjoyable. But if you were to roll the clock back 4 years ago when I first started, it was impossibly hard. Like I couldn't even get on the thing. And that's just because I hadn't developed the skills. And I think that as you start to master more and more things, it kind of becomes clear when something is objectively complex and something is subjectively difficult. So when I'm thinking about things and like parallel computing, I'm trying to differentiate these two spaces. Am I viewing it as like challenging because it's a subjective thing, or am I viewing it as challenging because it's just objectively challenging? And when I say that parallel computing was sort of it felt kind of impossibly hard. This is after I had spent some time thinking about it and I kind of understood, at least minimally, the basics of these things. At least I felt like I did. And so it wasn't impossibly hard because I couldn't do it. It was more like impossibly hard because I'm thinking about the reality of the universe and thinking, okay, if other people try to do this, wow, this is going to be like if people struggle today with C++, parallel computing in C++ is C++ on steroids. I mean, it is next level confusing. And I'm not for confusing. I'm for making things as simple as possible so we can do stuff, right? And prior to learning about transactional memory, I kind of thought this whole locking thing was you can do coarse grain locking, which is slow, but everybody kind of understands because it's easy to reason about. You just grab this lock and then you do some stuff and then you let go of the lock. And don't worry if you forget to let go of the lock, we'll let go of it for you or all this stuff, right? And then there's certain rules like scoped locks. You can't have like I forget the actual name for it now, but it's like you have to have structured locks, meaning when you acquire a lock, it has to release the lock at the same level of scope. You can't like grab it when you're 27 levels deep in a function and then release it 17 levels up above that. That's bad. That's bad because it's hard to reason about. And then people, person working over here in function 27 doesn't know about function 13 or whatever, right? So structured locks and then locks that potentially protect themselves from things like being re-entrant. So there's like re-entrant locks. This is all this stuff, but basically there's a certain like way to set up the lock at a coarse grain level, so it's easy, which is great. You can make it simple, but the problem is that generally is not fast. And if we go back to parallel computing and we think there's sort of two reasons to do parallel computing. One is to make it faster, and the other is to make it more convenient. If the goal is performance, then coarse grain locking is not getting us there, right? Okay, so then that leaves us with fine grain locking. And fine grain locking, just forget about it. Just like it is, I think, it falls into the space of being objectively complex because of all the stuff. And so even if you are a master in the subject matter, like so you're an expert in parallel computing, it doesn't matter, right? For example, when I was building my transactional memory systems, under the hood of the TM system, it's a massively fine-grained locking system. And I even overlooked I don't think it was a deadlock, but it was a race condition. Yeah. Which basically means that I messed up the locking, right? So there was a way that you could get into an inconsistent state, which says that I had a bug in my underlying system that was doing fine-grained locking, and I'm supposed to be an expert in this, right? Like that's what my PhD is on and stuff. So I can't get it right. How are other people that are non-experts supposed to get this right? So there's like a near 0% chance of that. So that was kind of my view of the state of parallel computing when I first started getting involved in it. And then I learned about transactional memory. And, as I think about these things, again, one of the core things I do is I just try to think about it from will this actually work? Does this make sense? Does this handle the issues that I think were present before, like the complexity and all this other stuff? And I kind of felt like it did. at least, at the high level. And then and I think Hans Bohm was also compelled, and he was working independent of me. Hans is significantly more senior than I am, and he was working in the space of research and parallel computing and garbage collection and all this stuff. Feel free to Google him. He's a superstar. It's pretty awesome working with him. But so we combined forces, I think when I was at Intel Labs, and then we decided to write this paper together to try to demonstrate why transactional memory is good. And I can't remember how we came across this, but we basically show in this paper that you can't really do generic programming in a really evolved, powerful way that's going to leverage parallel computing if you use locks. So let me say that one more time. You can't really do generic programming, so like templates or other things, if you are using locks at the core because of hidden behaviors that you may not be aware of, specifically the lack of guarantees on the ordering of acquisition of locks, because you kind of just like don't know what these things are under the hood. And we, here we have basically this deadlock and say, yeah, so here's how you'd get a deadlock. And then we basically show that if you have these template functions that are going to acquire locks under the hood that you don't know about, you can't really use these things in a general way that would leverage their potential performance benefits if they use locks, because fine-grained locking. Because fine-grained locking requires named locks, and named locks require a serial order of acquisition in order for the program not to deadlock. And so just, that's a little bit abstract, but just to make it a little bit more concrete, so it's just like this. So you have this thread 1, and then you have this thread 2, and this guy's executing, and it has to lock, we'll just call it 1, and then it has to lock 2, and then it has to lock 3. And the locks have to be acquired in this order. This is the serial order of acquisition of the locks. And if you don't follow this order, then the program can deadlock. This is sort of what you have to do with fine-grained locking. Now, it doesn't mean that you always have to acquire all the locks, but minimally, if you're going to acquire lock 1 and 2, you have to acquire them in this order. If you're going to acquire lock 2 and 3, you have to acquire in this order. And if you're going to acquire lock 1 and then 3, you have to acquire it this order, right? So, and then if you're going to get all 3 of them, it has to be this order. But now imagine that this is behind these various function calls. Like this is foo1, and this is like foo2, and so on and so forth. And then this other thread is going to call these things, but it's just going to call them like out of order. It's going to say, well, I want to do foo2 first, and then I want to do foo3, and then I want to do foo1. And for whatever reason, it doesn't release these locks until you do something like done with foo1, done with foo3. I think you probably get where I'm going. So, with fine-grained locks, the threads don't know that the locks are being acquired, and nor should they have to. And because of that, you can get the lock acquisition mixed up, and now you can deadlock this program. This is going to happen in generic programming, as we essentially demonstrate. And largely it's because of these callbacks that can get invoked. Oh, look at this. We missed a citation. Looks like I missed a couple. Okay. So, and part of that is through things like these operator overloading, right? Is that you can have, yeah, I think that was one of the key things. Try to show you can have these template functions, and then you can have something that looks innocuous. It just looks like, oh, this is probably fine. But then it turns out that this greater than operator invokes a user-defined greater than operator, and that acquires a lock or whatever, right? It's the callback stuff. And it, like with generic programming, it can call back into the user-defined code in ways that the generic programming system cannot know. Can't know. And that's actually part of the point of the generic code, is the generic code is, it's not supposed to know. It's supposed to say, look, we're going to write this generically, and then as long as you make your types work with these things, you're going to be good. But then they get implemented in a way that they do stuff that the generic systems didn't know about, and now you could potentially deadlock. And then we talk about all these things in this paper and show, hey, how this is how it could happen, so on and so forth. And then we basically show that when you do transactions, it sidesteps the issue entirely. And again, this is one of the best promises of transactional memory. The reason why I was so excited about it is one of the things that TM provides, TM system, it can essentially guarantee that your system is deadlock free. That's a really big and awesome property. That's super powerful. And for that reason alone, I get very excited about it. The second reason is it's just easy to think about. You can just say things like this, like, hey, this is going to be a transaction, and so execute this like a transaction. And why would you do this? Because you're basically saying this set operation might be a whole bunch of operations. Who knows? It could be like a million operations under the hood doing this assignment. So just make sure that it's all or nothing. Do the whole thing and only show the state of the program atomically after all of it's been set, or don't show it at all. Yeah, do it like before, but there's no intermediate state where half the object is set and half of it isn't, because that's invalid, right? And so that's why you wrap these things. And by the way, this is part of the reason why it's done in databases. You kind of just think of it as like the bank transaction. You take money from one account, you deposit it in the other account. There's no state where the money disappears from account one, but it's not in account two. That's the pretend universe. Where is the money if it's not in those two? It's like in this limbo state. No. There is no limbo state. When money is exchanging hands, it doesn't ever end up in in the air or in some black hole. It has to be one or the other. And the reason for that, the part of the reason why this is so important, is things like power outages or crashes or things like that, right? Think about it like this. You're in the middle of the transaction and you decide that, oh, it's okay if you have those three states. I can take it out and have it be subtracted there and be in this intermediate universe. Or I guess maybe it's just two states. So you have the original state where the accounts are exactly where they should be. And then you have this intermediate state where the money is taken out of account one, and then the money is in this limbo state and nothing is in account two. Then you have the third state where the money is actually in account 2, right? And the reason why this is bad is then if you crash the program or something bad happens in that middle state, the money has been taken from account 1, but it hasn't been deposited in account 2, so money gone. Money just vanished. That's not acceptable, right? Not for my money. Like minimally, I want to know that if I'm buying a new hoodie, that either it didn't go through or it did go through. Not this, you took my money, but they didn't get the money, right? So we already have transactions and they work great for distributed systems. So the second property is that they're very simple. So deadlock free. This is, property number 1, super cool. Property 2, simple. Property 3, can be fast. Can be fast. Doesn't necessarily mean that it will be fast, but it can be. If you do it right, it can be fast. And what's the evidence of this? Databases. Databases essentially are all transaction. I mean, for the most part, it's a transaction system. And so it has things like ACID. It's atomic, consistent, isolated, and durable. And TM is basically TM, well, depending on who you're talking to. Minimally, it has the atomic and the isolated part. Some TM systems are starting to be durable. And then consistency is really about the properties of the program. They're the preservation of invariance. It's probably different than what I think a lot of people, or at least what I originally thought consistent was. It's like, oh, it's a consistent state. So yeah, you start out with money here and you end up with money there. Like, okay, that sort of is an example of consistency, but the consistency part is really more about preserving program invariance. But let's not get into that. The higher order bits are that TM provides you potentially these things. And then from my lens of looking at parallel computing, parallel programs, when I was looking at this before transactional memory, first I thought that either you do it coarse grain or you do it fine grain. You do it coarse grain, what's the benefit performance-wise? So that's out. And you do it fine grain, one of the biggest problems is you can deadlock. Okay, so TM sidesteps that issue. That's great. Second issue that I had with fine grain locking, it's really complicated. Like you could make it work and you could make it fast, and let's assume you get away with deadlocks for now, but boy, is it complicated, and everybody has to follow the rules, right? And like, so these rules about this locking, you have to follow these. And what makes it even more challenging with fine grained locking is those rules. This is an example of invariance, by the way. These are program invariants, but there's no way that this is expressed. It's not captured in the program. So if somebody decides to not preserve this locking order, when you compile the program or you run it, it doesn't say, hey, you accidentally didn't preserve the locking order. You should lock like this. No. This is an implicit property in the program that I don't know that you can enforce at a compilation level. I mean, maybe you can, but it gets complicated once you have other components all contributing to this locking stuff, right? So part of the challenge is that it's very hard to enforce the implicit locking order that's expressed in the program. So with transactional memory, not only can it be deadlock free, but it's simple because you just say, hey, this is a transaction. And then it says, oh, it's a transaction. I guess that means that I have to minimally do this atomic and this isolated thing. Cool, I'll do that. And then you can do that all related to memory. Like it's actually quite interesting because it sort of goes back to his name's slipping my mind now. which is crazy. The Mike guy, what was this Mike guy? Mike Acton. So, oh, and by the way, I want to talk about like, would you guys, why are there so many dislikes? Like, I think I know why. And I want to talk about it. And I kind of get it. Anyway, I'm meandering here, but so as Mike was saying, one of the things that he kind of talked about was memory being really important. Transactional memory is basically doing the same thing. You know, he's talking about data, sorry, more generally. But when I think about data, uh, when I think about computing systems, I generally think about three things. I think about data, which is related to memory and stuff. I think about communication, and I think about compute. Those are, they call these the CDC properties: communication, data, compute. And the reason why I generally think about these three things is these three things tend to be the, hey buddy, yeah, you want to make an appearance? Here he is. Good boy. Okay, yes, we're almost done. All right, he wants to go for a WAOK. So with CDC, communication, data, compute, and the reason for this is these tend to be the key reasons for bottlenecks. So if you have a bottleneck in your system, I tend to find that it's probably in one of these three areas. Communication is, yeah, internet, Wi-Fi, sharing data. Uh-oh, now it's becoming the petting thing. The D part is data, but it's also related to memory hierarchies and stuff. And compute is basically the functional units that actually do stuff. So that do the multiply and the adds. So anyway, with transactional memory, what we generally found is with locking would block, it would be a critical section on operations. And I think this is part of the reason why like Morris is so brilliant is I think a lot of people, myself included, thought of these critical sections as like, here's this block of code. This is code. And you want to block this whole thing. So you can only have one thread of execution for this, which is how we did critical sections. And then you try to identify, well, where are the overlapping critical sections? And we would often say, oh, if it's shared memory, then that's kind of the thing. And that's exactly right, which gets to the heart of the issue is the things that you need to be synchronizing in the critical sections. When you think about code, it tends to be things that are related to operations in terms of compute. And then you have things that are operations related to data. These are the things, the data ones, that you actually need to synchronize on. Because just general compute stuff, you don't need to. Example of that is are things like GPUs, and why GPUs can run with zero synchronization and massively parallel is they have no shared data, not in those kernels. And so they execute in a super fast way because it's just compute operations. It's just this first piece. So anyway, because of this, this is one of the reasons why TM can potentially be even faster than fine-grained locking because it doesn't synchronize on operations in the general sense. It synchronizes just on data. So operations that are specific to data that can have conflicts. And for all those reasons, it seemed to me that transactional memory, at least from all the things that I had heard, it was sort of like, this is potentially the best thing that exists. Uh, which is why, walking down memory lane, which is why I leaned into transactional memory so much. This is also the reason why I lean very heavily into deterministic AI systems. Is I look at AI, and again, this is not to say that stochastic AI has no value. It does. I think stochastic AIs can be super valuable for almost anything that's not hard science. But then when it's hard science, I think you want deterministic AI. So what I was looking at in the world is in the space of ML, I was seeing a whole bunch of people doing stochastic machine learning, neural networks. And keep in mind, this was the thing that I kind of loved the most of all the ML things. So from my lens, it felt like, okay, well, that part's pretty well covered. What are we not covering? And so I just kind of took a step back and asked, are there things out there that we're not looking at right now that we need to pay attention to for this whole AI thing to work? And one of the most obvious was, could we build systems that could learn? And a big reason why you want learned systems is that they can scale in the knowledge that they can process significantly more than humans, just because machines are really good at crunching data or numbers or whatever, right? And so when we think about machine learning, one of the biggest reasons why we use them is their ability to ingest a whole bunch of data and then figure something out. So then on one hand, you have ML systems that can reason about a whole bunch of data and then do stochastic things. And I thought, okay, that's cool. But then it felt like, what about systems that can reason about a whole bunch of data, but then do deterministic things, right? Like things that it can actually come up with more concrete rules than to follow. Yeah. So all of this is essentially a little bit of background into why I kind of lean in to the things that I lean into. I kind of, at least from my view, I try very hard not to have an agenda. When I don't know stuff, I just try to look at it and say, this is interesting. Let me think about this a little bit and then try to figure out if it makes sense. So transactional memory made a ton of sense. Deterministic AI makes a ton of sense. And if I take a bigger step back now and I go back to the general space of parallel. No, we're almost done, buddy. Calm down. Just a little bit longer. He's had enough of this nonsense. So I look at parallel computing and I look at C++ or just any programming language. I do think that there are these asynchronous blocks that I see in things like JavaScript and other languages, and that kind of makes sense. But I'm not, I feel like there's more work to do. I don't I don't necessarily think that I know what the answer is. I do think transactional memory is, of all the things that I've seen, one of the most promising directions for parallel computing in the space where you want things to be done fast. And then when I think about asynchronous blocks, what I what I often think about, well, again, as we go back to this space of sort of the two reasons, did I not write it down? The two reasons of parallel computing, there's this fast, and then there's this convenient. No, buddy. I think of TM in the space of fast, and I think of like these async blocks as convenient. Because like the async blocks are basically saying, hey, I've got to do this thing, do this. and then let me know when you're done. This is like a convenience thing, right? It's not saying necessarily, I need this right now, stop the world. It's saying, hey, yeah, I need this thing to move forward, so you do it. And then it's almost like you're ordering from Uber Eats or something, right? It's all about the way that you're doing it. By definition, Uber Eats is not necessarily, I think, something that is urgent, because if it was super, super urgent, like it needed to be done right now, well, you would probably do it, right? Like if you literally needed food this second, you might just go to the kitchen and say, okay, or you might just drive yourself to the fast food place or something, right? You are invoking an asynchronous operation out of convenience, right? Or Amazon shopping and stuff. You're basically saying, yeah, I don't need this right immediately, but at some point it'd be great. So along those same lines, I still feel that this is something that is of importance. And I wanted to share this because given that things are maybe stalling with C++, or that we have a light version, like I think that's totally understandable. But from my lens, I probably am not going to be satisfied. Like I guess what I'm saying is I'll probably just continue to push until I think that C++ has something in both of these spaces. And a big reason for that, like one of the core fundamental drivers for this, is that due to the end of Dennard scaling, we can't just make single-threaded programs faster. This technology has run to saturation. We're at the peak of our logarithmic curve, right? We're here. It's not going up like this anymore. And because of that, parallel computing, especially in light cores that are on die, are probably one of the only ways that we're going to eke out that extra performance when we have shared memory. When you're working on things like that's completely SIMD, single instruction, multiple data, stuff that GPUs handle really well, yeah, just toss that over to your NVIDIA whatever processor, and it can handle that. But in cases where you have shared memory, those models don't, or those processors tend to not work that well, and so we likely need another solution. Okay. I think that I think that's all I'm gonna do today because this little guy needs needs his walk. So thanks everybody. But hopefully this sheds a little bit more light into some of the things that I've been thinking about, Hans has been thinking about, the transactional memory community is thinking about, and then just a general way that I kind of think about these things, just problems in general, I think from a scientific perspective, if that's helpful. All right, keep growing.